Um, so for the next video, we're going to be talking about energy, conservation of energy, potential energy and kinetic energy equations, and then we'll finish with going over example problem number 10. So first thing we'll do is just talk about potential energy and kinetic energy equations. So you can represent kinetic energy here, alright. Kinetic energy equals, you can see that, 1/2 mv squared. Potential energy equals mgh, and then sometimes there's energy coming from a spring or something like that, and that can be written as 1/2 kx squared. This is the spring constant, and x is like the displacement of the spring, so that would mean like how much x is pushed in. So say the spring is usually 2 centimeters, say we compress it to be 1.5, then x is going to equal 0.5. Alright, so now we're going to look, but for sometimes you don't need it, sometimes you won't need potential energy, sometimes you don't need kinetic energy, but we're just going to be worrying about these two in the example problem. But now what we're going to talk about is the conservation of energy. So pretty much what that says is that energy is never going to go away. It's just going to change what type of energy it is. So it's always going to be equal. So we can represent that as 1/2 mv squared plus mgh, what it starts out as, and then any changes, the sum is still going to be equal. So 1/2 mv squared plus mgh. So that right there is conservation. So we just went over conservation of energy, and now we're going to look at it in a problem. So I'll just show you this to read for a second. Pretty much particle A hits particle B. B is not moving. And the force can be represented by that. R is the distance between the two particles. A is located at 2D, and B is located at 0. So pretty much what the question is which of the following equations could be used to find R minimum? The minimum distance between the masses as a particle A approaches particle B. Okay, so this shouldn't be too difficult. So first off, we're gonna set it up, because it looks like all the answers are potential energy equation. Are conservation of energy equations. So we're gonna start by using what initially is there. So 1/2 mv naught, that makes sense as our as one of our energy equations. And then on this side we use this constant, U equals B over R squared, but instead of R we can use D squared. So we plug that in here. So, and we know R, in this equation we can represent R equals 2D initially, right? So it's going to be over 2d squared is 4d squared, and then plus 1/2 mv naught squared, and then that's going to have to be equal to this positive constant. So we can use that again over here. So instead of over 4d this time, it's just gonna be r minimum squared. So r squared min. Then here, once they get super close, first off, now it's a 2-particle system where one is moving. So instead of it being 1/2, it's 1/2 times 2. I'm talking about m, so it's just m instead of 1/2 m. And then we know that like the total velocity, because of conservation of momentum, it's gonna remain equal. So we know this equation is m1 v1 equals m2 v2. So pretty much all we have to do for this is we know that's going to be true. So if initially one was at rest and one had a velocity, we know that at this point, at the minimum distance, they're going to be at an equal speed. So we're just going to use v naught plus m times v naught over 2 and then have that square. So we can look here and we find that in answer B. So that's our answer. Yeah.